Alright, welcome back to the Flight Zone. Last episode, we went over what you need to get started in flight school, and now we're starting flight school. So, today we're going to be going over some helicopter aerodynamics. This is going to be part one of maybe 2 or 3 videos, because I could probably cover it all in one video, but the last video was kind of long, and I'd like to keep them kind of short, sweet, and to the point. So, my name is Caben Hansen. This is my channel, The Flight Zone. Let's go ahead and jump right into it. So, there are 4 forces acting on an aircraft when airborne. You've got thrust, which is the force of the aircraft propelling itself forward. You have lift, which is in our case, the helicopter lifting itself into the air. And thrust and lift are what we're using to combat drag and weight. Weight is, of course, what's pulling us back towards the earth. So that is a culmination of the helicopter itself, people, occupants inside, luggage, fuel, etc. Drag is an aerodynamic phenomenon, I guess you could say. Everything that is not producing lift are producing drag. So you got, say, like the canopy. You know, if you're flying forward, air that's coming this way and hitting the canopy, that's drag. It's slowing the helicopter down. And that goes with everything. Everything that air is hitting on the helicopter that is not turning into lift ends up being drag. So we're going to go over some of this here right about now. Lift. How does it work? Great question. So the concept of lift is it's got to do kind of with fluid dynamics. So what we've got here is Bernoulli's principle. And basically, what Bernoulli's principle is, air moves faster in an area of low pressure. So think of like a hurricane, or even a tornado. Those are basically just giant low pressure systems. I know we're not getting into weather just yet, but just an example. And what kind of winds do tornadoes and hurricanes, what are they kind of associated with? That's some high velocity air. Check it out right here. High velocity airflow. Bernoulli's principle. Air moves more quickly over the curved upper surface of the wing, or the rotor blade, which is basically a spinning wing, than it does under the wing, which has a flatter surface. Lift is created approximately 70% by the low pressure over the airfoil. So, just in case y'all didn't know, it's kind of cool. With planes, I think there's a common misconception that high pressure under the wings is actually what pushes a plane up, or even a helicopter up. That's actually not fully the case. Not even half the case. The 70% of the case, it's more so getting sucked into the air because there is low pressure going over the top of the wing. Because of this slope here, the air that is flying this way, so see it says direction of flight, and you've got your arrows with the air coming here. There's low pressure here because air basically can't stick to that wing. So it's, for lack of better terms, I don't want to use the term vacuum, but it's, the pressure is a lot lower on the top of the wing. I'm going to just leave it at that because I don't want to confuse anyone. Low pressure over the top of the wing, high pressure onto the bottom. That low pressure up here kind of sucks the aircraft into the air. So here's where the other 30% comes into play. And this is what I believe most people think is how an aircraft flies. It's through Newton's third law, which states for every action, there's an equal and opposite reaction. So that high air pressure that we were just talking about, that goes under the bottom of the wing, hits the wing, pushing it upward. And so it sort of assists Bernoulli's principle. Newton's third law is just assisting Bernoulli's principle. So kind of cool. You learn something new every single day. And if you've learned something right here, click that like button for me. I would appreciate it. Alright, angle of attack. Angle of the airfoil, so there can be the wing of a plane or the rotor blade of a helicopter, in relation to relative wind. So, relative wind is basically the direction of the air in relation to the airfoil, so the wing or the rotor blade. So if we look at this picture over here, it's a pretty decent example. This plane is actually flying along this dotted line, but its nose is pointed up here. So this is our angle of attack. It is the angle at which the air is actually striking the airfoil. If, as I've written here, if the angle of attack becomes too great, the airfoil will stall, so it won't actually be able to generate any more lift. So, as a lot of this air is flying over these airfoils, and remember what we discussed a couple of slides ago, that's how 70% of our lift is created, is through air going over the top. So when that starts to suffer, when we're not getting a lot of airflow up there, and this 30% is all we got, but that pressure is kind of like starting to get pushed to the front of us, we're gonna stall. So we're gonna kind of use that airplane. That's a pretty good example. The same thing can happen with helicopters. We'll learn about something called retreating blade stall a bit later on, probably in another video. So now that we've got angle of attack out of the way, let's move on to the lift formula. So CL, this is actually the coefficient of lift, which is entirely determined by the wing shape. Every wing shape has its own properties. That includes the actual shape of the airfoil, not like that teardrop that we were just looking at. So this right here, the shape of this can heavily affect the coefficient of lift, as well as the angle of attack. So, the wing shape divided by the angle of attack, and the angle of attack, the lower it is, the better. So, like in this scenario right here, where we have a really high angle of attack, the wing shape has to get divided by that, and so that's going to make that number a lot smaller if the denominator is smaller, your AOA. So, and if we want a lot of lift, we want these numbers to be big, but you got to be careful. Any number that's zero, any number multiplied by zero is zero. So, for example, v, velocity squared, if that's zero, we're not generating any lift. But cabin, if there's a lot of wind, can't an airplane technically be lifted off the ground? Yes, it can. This velocity is actually referring to air velocity. So keep that in mind. P, pressure, or air density, they're different, but that's the symbol they used. Don't know the name of that. And then wing surface area. Kinda sorta goes with wing shape, but this is actually how big the wing is. So that's useful too. And then you divide the whole thing by 2. I didn't really have to use this that much when I was in training, but it's important to know that formula, I suppose. Alright, drag. This is one of our other forces. There's a few different types of drag. They're basically all right here, and before I start going over those, they actually all act a little bit different. And you add each of them up at any given point to come up with your total drag. So at any given point, what I meant was forward speed. So we're at 0. We're going to have a pretty good amount of induced drag. Well, let's go back. What is that? Or let's talk about profile drag first. Profile drag is frictional resistance of the blades passing through the air. With a plane, it would be its wings. Increases moderately with speed. So this is literally just the friction of the air across your airfoils. Not a whole lot we can do about that. The faster you go, the greater that air friction is going to be. Induced drag, product of lift generation. So, I should have put a picture of this. Let's see. Airliner vortices. I don't know how to spell. So right here, we see this plane, this 777, and we see these kind of tornado-looking things off of its wings. These are vortices. And vortices are a product of lift generation. What's going to happen with these vortices? They're going to develop most effectively with aircraft that are generating lift, obviously, that are heavy, and they're slow, and they're clean. So basically, borderline stall. Like, not really, but you get the idea. Slow lift. Now, why am I bringing this up? These vortices, believe it or not, almost act as if they're attached to the aircraft. They cause drag for the aircraft that is creating them. I know, it's crazy, right? Same thing with a helicopter. Just like that. So these vortices act as drag for the helicopter. That is induced drag. Can be decreased with higher airspeed as the angle of attack decreases. So yeah, if you lower that angle of attack and go forward really fast, that induced drag reduces drastically. It's aerodynamics for you. Parasite drag. I kind of associate this one with cars a lot. I think it's kind of a limiter with a lot of cars' top speeds. You know, like in the real world, you know, we got some fast cars out there today. You got like really powerful like Bugattis and Koenigsegg's and stuff like that. You're really high-end, top-of-the-line stuff, but they all seem to kind of have they kind of plateau at that 300 mile an hour range. Well, that's because of parasite drag. Increases with airspeed, caused by air deflection of all non-lifting components of the aircraft. So this is your key part. Increases with airspeed. Increases drastically. So the faster you go, especially with the air being dense, so if you're closer to the surface, like closer to sea level and not like, say, super ridiculously high up, like 50, 60, 70,000 feet, then your parasite drag is going to be pretty intense. So with each of these, at each of their specific points during forward airspeed, will create your total drag. And technically, right here, when your drag is at the lowest, that is when you are most efficient. And that can vary aircraft to aircraft. Alright, we've got our other two forces acting on the aircraft. That would be weight and thrust. Weight. As I mentioned earlier, it's the entire weight of the aircraft. This includes the aircraft itself, crew, passengers, luggage, fuel, etc. Weight opposes lift. And it never stops, unfortunately. So, as long as you are airborne, you are fighting weight. Thrust. Produced by the rotor blades to move the helicopter laterally. Thrust opposes drag. Alright, let's move on. Rotor systems, configurations, and counter torque. Pretty cool. So, with helicopters, there are three common rotor systems that are often utilized across different models of helicopters. With the Robinson R22 and the R44, they're going to be using what's called a semi-rigid rotor system. And we'll go over that in just a minute. Rigid rotor systems are very stiff and don't have a lot of... They're very nimble and they're easy to control, but they are... They don't quite move quite like a semi-rigid system can, or even a fully articulated system. A fully articulated system is the most complex, and we'll talk about that in a minute too, as well as rigid. Depending on the system, as I mentioned briefly, blades may teeter or flap, lead and lag, and or feather. Now, what does any of that mean? Feathering. Blade pitch can be changed. all helicopters can feather. So when you pull up your collective with your left hand, you are feathering the blades. You are changing the pitch of the blades. Flapping is more common with two-bladed helicopters. Basically, the blades can tilt. So as one blade goes up, like if you're outside the helicopter doing your pre-flight and you push one blade up, the one on the opposite side is going to go down. And that's actually important in another part of aerodynamics later. We will get to that. It kind of helps with the symmetry of lift. Lead and lag. What does that mean? It means that blades can move back and forth during rotation. This is only incorporated into fully articulated aircraft. So let's move on to semi-rigid. We'll get a bit more into that. Semi-rigid. Like I mentioned, they're usually composed of two blades, like with the R-22s and R-44s. We got a picture of a beautiful R-22 that I have personally flown. It's one of my favorite ones. And yeah, it's got two blades. Basically, with a semi-rigid system, the blades are rigidly mounted to the rotor hub. But, as I mentioned, if you push one up, the other will go down, so they're not completely rigid. They can tilt with respect to the hub. The only real risk with a semi-rigid system, and it seems to be actually most common with Robinson helicopters, unfortunately, risk of mast bumping. What's mast bumping? So, that's when the rotor system actually hits the mast. And that can destroy the blades, and you can become a rock kind of falling out of the sky. Very dangerous. Caused by excessive flapping from low-G maneuvers. So maybe you push that collective down, and you push that nose forward, and maybe your main rotor blades, they blew back. But because it's on a teeter hinge, they can almost move as far as they want. This is a pretty good example here. Here's your mast, and here's your rotor blades, and here's that teeter hinge. Well, if that teeter hinge moves too far, the rotor system can actually hit the mast, which is no bueno. Caused from low-G maneuvers or abrupt changes in cyclic control. Not just abrupt, but abrupt and excessive. So you kind of have to push it pretty far. The semi-rigid system can feather and flap, so we kind of knew that. You pull up on the collective, that'll change the pitch of the blades, and they can flap, so they can teeter. They have their teeter hinge. Example, our Robinson R-22. Alright, that's a pretty crazy picture. Sorry for the low res on it, but what is a rigid system? They are mechanically simple but structurally complex. Operating load is absorbed entirely in the bending of the blades. And as you can imagine, the blades are very, very strong. I mean, just look at this. This is not an exaggeration of a picture. We can look it up. The Red Bull BO 105. These guys are crazy. They literally do all sorts of crazy stuff with this helicopter. And it utilizes a rigid system. It's very responsive, and it's extremely strong. So, they cannot flap, or lead, or lag. They specifically feather. So, I don't want to pretend like I even know how the cyclic linkages work in this, but they're able to do some crazy stuff. These blades are often really expensive, as I mentioned, because they take absolutely all the beating. I hear that blades, just for this helicopter alone, just a set can run close to $1 million. So, it's pretty insane. Alright, last but not least, fully articulated rotor systems. This is kind of a good image that might have helped earlier. So, if I didn't explain leading and lagging very well, so leading and lagging is the actual lateral movement. There's a hinge, a lag hinge, as you can see. So the blades can actually move independently Yeah, this is flapping, moving up and down. Feathering is being able to twist. And then lagging is moving forward and back. These are definitely the most mechanically complex. Fully articulated, they can do all of the above. They can lead, lag, flap, and feather. These are found on helicopters with more than 2 rotor blades. So I've actually got a picture here. This is a Schweizer S300C. Similar to the R22 in terms of like power plant and size. They use the same engine, or at least the Beta 2 Robinson R22, as a Lycoming 0360. The main risk with fully articulated systems is ground resonance, which doesn't really mean anything when you're flying. If the ground is bumped too hard upon landing, the blades can lead and lag out of balance, and the helicopter can violently begin to shake. It can be corrected by immediately taking off again. The center of gravity is thrown off, essentially. Yeah, this is actually a part of a television show, and in the show that they were shooting, they had an actual helicopter, I think, drop off maybe some of the cast. So here's the helicopter, and you'll notice he starts shaking, like after he drops his passengers off. So see how it's starting to shake kind of violently? He fixed it just by taking off. That was ground resonance. Rotor configurations. This stuff's kind of cool. So, aside from a traditional rotor system with a main rotor blade and a tail rotor, or main rotor blades and a tail rotor blades, some helicopters have different rotor configurations that completely eliminate the need for a tail rotor altogether. You have tandem, coaxial, and intermesh systems, each unique in their own way. The tandem configuration. So, it's pretty simple, not really, but it's 2 sets of blades mounted on separate axes on top of the helicopter. So here's a CH-46 Sea Knight. As you can see, there are 2 sets of blades on top of the helicopter. They spin in opposite directions, canceling out the torque altogether. So there's no need for a tail rotor to constantly be pushing in a singular direction. Kind of cool. Alright, coaxial configuration. These are, in fact, more common on Russian helicopters. This is a picture of a Kamov Ka-52. This is a Russian attack helicopter. A little complex, but there are some planes out there that use this similar concept with 2 propellers kind of stacked on top of each other, spinning opposite directions. The main difference here, it's still 2 sets of rotors on top of the helicopter, but they share an axis. So if you know anything about turbine engines, you could sort of see this similar to there's a shaft that spins and there's a shaft that's stationary. But in this case, neither of them is stationary. One of them just spins the opposite direction. So it's kind of interesting. I always thought that this sort of design was pretty cool. They spin opposite directions, so that cancels out the torque once again, and it works. Alright, this last one sometimes scares some people. It's not very common, but just looking at it, you might think it's kind of a mess. Well, let me explain. Intermesh rotor configuration. These blades can actually never come into contact with each other because the masts, or the actual shafts, have gears on them, and they're geared with each other. And so, the only way these blades could ever touch is if the gears somehow skipped a ton of teeth, which is practically impossible. The blades are slightly angled, so they don't pull straight up, and they actually don't pull with each other. So they're almost, you can see they're kind of pulling away from each other, but they can't be at the same angle because then they would hit each other. So keep that in mind. But because of this, rotor efficiency is slightly reduced. This helicopter here is the Cayman K-Max. Pretty cool. I believe the Air Force had a I think it was called a H43. I think also made by Cayman. The HH43. Wait. Yeah. The Husky. Oh, there's a Marine one too. I think these were used for firefighting. It's pretty cool. Pretty cool machine here. Pretty interesting piece of history. So yeah, that's what's up. That's some cool stuff. I didn't need to know rotor configurations too much, but you might. So there they are. Alright guys, so that's it. My name is Caven Hansen. Thanks again for watching. If you liked it, please leave a like, leave a comment if there's anything I can help you with. I'm still kind of coming over some, I guess, recording anxiety, I guess. But I'm trying my best. And yeah, that's all from the Flight Zone today. You all take care, and I'll see you all in the next one. Bye-bye.